Hello, everybody, and welcome to episode 61 of the Hyperthesis podcast. I'm Liam.
I'm Feely. I'm Patrick.
Today, we're joined by a very special guest, Alex Kayssi, who's currently a PhD student at McMaster University. A little quick introduction to Alex. He completed his Bachelor of Science at McMaster University, where he conducted undergraduate research in solid-state materials physics. And additionally, he completed his undergraduate thesis on the stability of black hole metrics. So he did a little bit of different stuff during his undergrad, not just one topic, which is always good. Right now, he's completing, well, I said his PhD, I meant his master's, but I'm assuming he'll continue with his PhD. Right now, he's completing his Master's of Science at McMaster University, working for Dr. Sergei Sibinarikov, which we actually had another guest, Andrew, who worked for Sergei as well. So this is the second Sergei student we've had as a guest. And right now, Alex, you study theoretical cosmology on large-scale structure of the universe and the statistics of how matter is distributed throughout it, if I got that correct.
Yeah, you got that.
Oh, are you the ones solving the dark matter problem?
Oh, not entirely, but I would like to.
Well, thank you very much for joining us. And before we ask you about your life and work and hopes and dreams and all that, I have an intro topic, which is mostly just a correction, actually. So in episode 59, I said a lot of things that I wasn't 100% sure about, and I said I wasn't 100% sure about them, but I came back and I wanted to kind of talk about it a bit more and be a bit more concrete. So I commented on how the age of the universe, according to our current theory, is around 14 billion years old. And I talked about how you can calculate that for a particular special reference frame. And I think I used the language, I called that reference frame an absolute reference frame. But there is no general relativity tells you that there is no such thing as an absolute reference frame. Everything's relative, right? So I think the correct wording I should have used was that there's a kind of a special or a more natural reference frame to use where the math is easier or things are a bit nicer than they would be in other frames. Oh, so relativity tells us that there's nothing wrong with having special reference frames as long as the laws of physics aren't different in them. So the special reference frame where I mean, Alex, you might know more about this than I do, but I think when they calculate the age of the universe, well, you can actually determine it experimentally by looking at the cosmic microwave background. But also, the cosmic microwave background from our point of view is anisotropic. So depending where you look, it looks different. Whereas there's this particular natural reference frame of the universe where the cosmic microwave background, if you are in that particular reference frame, it is completely isotropic. So no matter where you look, the cosmic microwave background looks the same. So I think when you calculate the age of the universe to be like 14 billion years old, you can do it from that reference frame. Maybe?
Well, I know there's actually like more of I think, theoretical way of being able to calculate the age of the universe, because in reality, we know that for the majority of space-time seems to be like homogeneous and isotropic on large enough scales. And so if you sort of try and write down the equations of Einstein's field equations for something that's homogeneous and isotropic, you get like an equations of motion kind of for the universe, and those are called like the Friedmann equations. And from that, you're actually able to sort of, do some math and do some integrals, and eventually find out that you can actually calculate the age of the universe through sort of these calculations for like if the universe, because the universe is kind of expanding, so you can kind of say, given plugging in all the values and parameters that we measure for the universe today, what should the age of the universe have been when you do all of that math? And so I know experimentally, I think that's probably just like a way to verify it, but I don't really know. As far as I know, I don't really think there's a way to do it to the CMB, because the CMB I know has a certain like we know how long ago it was. But before that, we don't know anything, and so I don't know if we can really say anything about the age of the universe behind it.
Okay.
Yeah.
I guess
I
you
don't-
can say like up until 100,000 years or so. Like doesn't the cosmic microwave background, didn't it form according to our theory around 100,000 or so years after the supposed Big Bang?
About, yeah, but everything before that is like we don't really know anything because at least not through experiments, because the CMB's got blocking that. Because the entire thing about the
Hmm.
CMB is that everything before that was too opaque for any sort of like light to be transmitted through there. Because like the when the Big Bang was first happened, everything was so hot that light was scattering off everywhere. It wasn't it would We didn't really have a chance for light to easily move through and just to kind of have like a transparent looking universe. And the CMB is sort of like that last surface that we kind of see right when the universe is sort of becoming transparent. And so, but if everything before that, at least experimentally or observationally, we can't really say much about aside from maybe theoretical experiments or sorry through theoretical calculus.
Yeah, so
So they're all just modeling and guessing
Yeah,
and
essentially.
everything. For the, like, I'm not a huge Big Bang believer, but I think there are some problems with the Big Bang theory. But it's a reasonable proposal, right? Like when you see, oh, it's expanding. If you do time reversal, it's much go back to a point. Like, okay, you know what? There's some sense to it.
Yeah, well, actually, it's funny you say that because it's not really the Big Bang, I think, that's disputed, but really more of like the inflation immediately after the Big Bang that's inflated, because uh, you can sort of argue that because like we know that like the CMB was actually sort of like the final smoking gun evidence that we had for the Big Bang existing, because it was a hot, dense universe, exactly what we would have predicted if we had a Big Bang. But if you actually sort of like look more on the inflationary sides, you can find that you have some weird scenarios, or it can lead to some weird scenarios, such as something called bounce cosmology, where if there was a previous universe before, for some reason it went through some phase of shrinking and eventually reached like a small minimum point until it eventually burst out again, uh, and sort of like the universe was sort of rebirthed like that. So I guess in that sense, you can kind of say the Big Bang doesn't exist, but uh,
Or
I'd
there's
say
kind of like a supernova, right? Stars die and like they collapse into one and then just explode, kind of type, but in the
yeah.
universe instead.
Yeah, I think definitely, yeah, exactly. I think like in that sense, like a lot of people agree that the universe was very small at one point, but whether it was like a singularity, like you said, or if it was actually something big that shrunk to its minimum size and then bounced up again, then that's up for debate still, I think. I
I'm
would say
a
at least, but
I'm a firm non-believer in singularities.
yeah.
So whenever you have a singularity, it means your theory is wrong or it's missing something, at least
Hmm.
as far as I'm concerned. But maybe there is a true singularity, who knows, but I doubt it.
I know that was a common, I guess, debate maybe 2 decades ago, a decade ago, where will the universe end in a big crunch? And now we kind of accepted kind of the heat death of the universe, where it will just kind of keep expanding and go on forever. But I still kind of like the idea of a big crunch as one being maybe the end of the universe someday, and also the start of the universe. Because if you have this big crunch, all this energy's maybe not necessarily going into a singularity, to not upset Liam, but instead going into this something and then re-expanding again. So, I mean, big crunch fans, let's hear it.
Well, I think when I think about it too, when if the heat death universe happened, right? It is so everything's kind of flattened out, spread out that you wouldn't be able to tell if it's crunch or if it's flattened out. If it's so nothing, right? Like how could you tell it's not a point?
Anyway, so yeah, so I think what I was talking about in episode 59, relating to what Alex said, is you take these equations from general relativity, and you can calculate what the age of the universe should be. And I think they do it in these special co-moving coordinates, or these special coordinates where from that frame of reference, everything looks isotropic. Um, so that's kind of what I was talking about in episode 59. And one other thing I was talking about was that I didn't really do this thing called false vacuum decay. Well, actually, we talked about false vacuum decay in the vacuum catastrophe problem came up, and I don't know too much about it, so I kind of I think I said a few comments on it and then end it with I'm not really sure. I'll come back to this later. So I just wanted to comment on that and do it a bit more justice. So there's this problem called the vacuum catastrophe problem, or the cosmological constant problem, which is this huge disagreement between the observed values of the vacuum energy density of our universe, otherwise known as the cosmological constant. And so there's a huge disagreement between what we experimentally see and what we should theoretically predict based on quantum field theory, which is, we've talked about this before. It's, a really good theory, it turns out. But when you do the experiments, you predict that the vacuum energy density of free space should be around 10 to the minus 9 joules per meter cubed, something like that. You can use different units, but those are the ones I used when I looked it up. And it's pretty small, like you might expect. And you can actually determine this based on experiments that involve spontaneous emission, the Casimir effect, and this thing called the Lamb shift, which are all these effects that you need QFT to describe. And I think I mentioned that in episode 59. I mentioned at least one or two of them. So 10 to the negative 9 joules per meter cubed, that's roughly the energy density you should get of the vacuum. And for reference, if you do a little back of the envelope calculation, because I always like to do this, if you have an apple, there's about 95 calories. You convert that to joules, that's about 400 joules. The volume of an apple is around 270 centimeters cubed. I just Googled this stuff, but I'm sure it varies widely, but just from Google, you can calculate the energy density of an apple to be around 10 to the 6 joules per meter cubed. So that's about 10 to the 15 times bigger than the energy density of the vacuum that we experimentally see. However, when you do quantum field theory, so you use our best theory that we have so far to try and predict what the vacuum energy should be, you get around 10 to the 40 to 10 to the 110 joules per meter cubed. So you get about 50 to 120 orders of magnitude greater than what you experimentally see. And this has been called, quote, the largest discrepancy between theory and experiment in all of science, and the worst theoretical prediction in the history of physics. So even though quantum field theory works super well a lot of the time, for some reason there's this vacuum catastrophe problem with this huge disagreement. So it has to do with the fact that gravity and quantum mechanics don't work well together, which we talk about all the time.
Sorry, just a quick correction. You said the energy density of an apple is about 15 times that of the experimentally confirmed vacuum energy. 15 orders of magnitude. Yes, 15 times would be scary, one way or another.
Yes, I meant 15 orders of magnitude, so 10 to the 15 times greater. A lot of zeros. So yeah, I just wanted to comment on that to get the point across a bit more. So physicists have a lot of work to do, it turns out.
I will also say this is a win for experimentalists.
Yeah, I don't actually know the details of how they experimentally determine that. So maybe they're wrong, but I mean, they're probably more right than the theory is, honestly. Anyway, so that was the intro topic, and now we can move on to the main topic, which is our wonderful guest, Alex. You are the main topic.
Yeah.
So, Alex, can you tell us about what you're doing at McMaster right now for your master's thesis? So what research do you do?
So I think kind of like how you put it earlier on, I'm kind of studying the distribution of matter on large scales. And that might seem a little bit sort of like or how do I say? Like I know every time I describe this, I feel like it's a little bit odd to explain why we're doing this, but I find like it's so interesting once you actually go into the deep physics. Because the reason why studying this sort of like the way that matter is distributed on large scales is because we know going back to inflation that inflation is supposed to describe why the universe that we see is supposed to be like flat and homogeneous. But the issue with that is that it actually does that job a little bit too well, up to the point where if we had inflation and only inflation, then the universe would be kind of too smooth for any sort of clumping of matter to form under the gravity. And I think it's like to the point where we wouldn't even have sort of large scale structure that exists today, which forms like, galaxies and planets and everything. And so the way that we remedy this is to introduce the fact that we have sort of quantum fluctuations that happen near the end of inflation, such that these small fluctuations actually sort of perturb matter in such a way, in a way that now we don't have a perfectly homogeneous background, but it's homogeneous enough to agree with what we see today on large enough scales, but inhomogeneous enough that we can sort of have clustering of matter that essentially starts to like get influenced with each other under gravity and cluster up and essentially form these planets and galaxies and just matter distribution that we do see today. And so, I think that's a question.
Oh, I was gonna say, so without these, so going back a bit, you have no, if you have no quantum fluctuations, pretend we don't know about them. If you do all this general relativity stuff, you find that the universe should be isotropic, so it should be the density should be constant. But you say that you mean like on large scales, right? So if you zoom out really far, the density is roughly constant. But like a galaxy, like I guess the universe isn't constant. It's not a constant density. But can you not describe that with GR? And you have to kind of put these quantum fluctuations in to deal with it, or how's that work?
It sounds like we have this clustering, right? Like, well, if we model everything as smooth, there wouldn't be clustering which forms stars and galaxies. So there must be something in the mass distribution that contributes to this, the why stars are formed in addition to this smooth universe.
Yeah, exactly. Because we can't have it that the universe is too smooth to the point that matter hasn't had enough time to sort of gravitate or self-gravitate and sort of form these like large structure, form these structures that we see, including galaxies and everything. So we kind of need to include these quantum fluctuations because these first of all, they're sort of like well accepted that there should be quantum fluctuations because of the uncertainty principle and everything. But at the same time, these also seem to be exactly big enough that they sort of give us enough of a more or less matter in certain places that they can start to self-gravitate and form these sort of like structures over like large, like these galactic filaments you might see in these like pictures of like a large scale structure, or if you even look small enough, like these galaxies and planets that we see.
So how does this work? Do you work with, let's say, like a master equation, try to dynamically evolve that, or is this more like a simulation that you run, like numerical simulations?
So the way traditionally it's been done is you sort of assume that, once you have assuming you have your perturbations already there, you kind of want to study how these perturbations evolve over time. And then the way that you can even just like formulate, like the way that you can even mathematically generate these perturbations are just sort of like taking your equations for inflation and sort of adding a small perturbation term in them, and then all of a sudden you can do your regular physics and figure out what the equations of motions for these perturbations are. And so that's kind of how we have an idea, like what the general form, or that's how we kind of get an idea for like how these perturbations kind of behave early in the universe. But afterwards, when we want to study more how they evolve throughout the entire evolution of the universe, like after inflation ends, and we go through our standards expansion of the universe, then we kind of have this traditional approach of treating everything as a fluid, more or less. And so you can kind of apply, especially if you look on scales that are like within the observable universe, then Newton, and because matter sort of behaves very slowly compared to like your relativistic stuff, you can kind of apply regular Newtonian gravity and regular fluid dynamics to your perturbations, and now kind of study like the motion of matter as it clumps as just a fluid which is coupled to gravity and is influenced by the movement of gravity.
Well, can you clarify what you mean by inflation equation? Like what do you mean by that? Like, what do they describe? Like, is this describe a ball? Like I'm just trying to understand what is inflation equation.
Sorry, sorry. Yeah, I should have probably explained that a bit more. Because we know that inflation typically we can describe it as a rapid expansion in space. Oh, space. Yeah, in space. And so if we want to try and formulate that better using quantum mechanics, then you just do your regular quantum field theory and throw a scalar field at it and treat sort of like the mechanism of inflation as a scalar field. And what you actually find is in order for a quantum field to sort of drive inflation, like sort of give it the energy that it needs to really expand really quickly, is that kind of needs to follow something called like the slow roll parameter, where you end up having like a very, very flat top for the potential, and so the quantum field sort of like has a lot of potential energy but doesn't move a lot. But then as the quantum field, which is called the inflaton, by the way, sort of like gains more and more kinetic energy, that actually kind of ends up sort of mathematically being a slowing down of the inflation. So while you
So it
are
described the boundary of the universe. Is it like the evolution of the boundary of the universe, or what's inside
or
it?
it's just the like it sort of provides like the energy that you need for this acceleration, really. Because like I think in order for inflation to happen, you kind of need this rapid outward acceleration happening, and so in order for that to get the energy, you kind of have this quantum field which is sourcing this energy, which is sort of like putting energy into the universe for it to accelerate outwards. And so while this while you have a lot of energy in the scalar field or this quantum field, the universe is accelerating a lot. But then the second that this field sort of loses all its energy, that sort of like comes down to the universe slowing down. And that's kind of where you go back to your regular Big Bang cosmology from that we kind of been accepted before.
So I remember we took this QFT in curved space-time class with Sergey at Perimeter. And although he talked about inflation for the last couple weeks, I did not pay as much attention as I should have because I was doing it over Zoom, I think, at that time for some reason. But basically, we don't have a theory of quantum gravity, or else we would just do that. So you have to be careful. And I remember you always do this minimal coupling, is what they call it. So you take your quantum field theory, which is it's like you take quantum mechanics, but now you can now have changing numbers of particles due to the fact that, oh my god, my cat. Oh, sorry, my cat jumped on my computer setup. So you take these quantum fields and you minimally couple them to classical gravity, which is just a fancy way of saying you're trying to calculate how curved space-time influences the quantum fields. And I think for like standard inflation, you're doing the same thing, right? You're saying general relativity gives you these specific equations that describe inflation, so the Big Bang, and what happens when you take the vacuum of space at one instant, very early in the Big Bang, and say this quantum fields, these vacuum modes or whatever, when they're coupled to this curved space-time, to these Einstein equations, how do they change as time goes on, and how do these little vacuum fluctuations in them influence the matter as space-time expands? Maybe. I kind of know what I want to say, but I'm having a hard time wording it.
Yeah, it's almost trying to remember exactly how the course was, or how they phrased it in the course. But yeah, it's kind of like that same idea where we have these quantum fields that are coupled to gravity, and then you have your whole like action or Lagrangian. Uh, but then that's actually kind of like a good starting point to what I was talking about before, because if you have these quantum fields, then adding these small perturbations to these scalar fields is the same quantum fluctuations that we're studying in this case. Because like typically, like you said, you have some scalar field and it's coupled to gravity. But then if you add like a small variation or a small delta phi for the change in your field, and you do your regular like or Lagrange stuff or regular physics, then that's how you get the equations of motion for kind of studying how these perturbations change over time.
Yeah, we do this in ultra cold physics all the time, actually. Um, I guess the simplest way is like you can imagine you have like a pool of water and it's flat. There's no waves in it. It's just motionless. And you put, I don't know, you like make a small wave in it, and the wave travels through the water. You could do fluid mechanics and describe all the water in the pool, but that's kind of unnecessary. You can actually just ignore the kind of background water that's not moving and just describe the little wave of water on its own. So you can kind of describe that small perturbation through its own wave equation instead of working with like a fluid mechanics equation that describes all of the water in the pool. And I think it's the same thing. I mean, mathematically, you say you linearize it or whatever. You take a first order perturbative expansion for the physicists out there.
Well, I feel like conversation is getting into very advanced stuff, so I'm gonna kind of ground it a little bit because, like, a lot of physics, well, a lot of physics that physicists do is basically have something that are simple or not. Well, simple would be wrong, but like let's say like homogeneous and uniform and easier to describe, and we make this perturbation, which just mean we disturb it a little bit, right? And we want to describe how this perturbation evolve, and a lot of physics come out of that because we like something that is linear. We love it when it's linear, but we know nature, most things in nature are not linear. And how do we describe that? And even Taylor expansion in a bit, it's like perturbation, right? You want to see what's around that point. That's why we do Taylor expansion, and a lot of theory papers just doing Taylor expansion on known theories and just publish a new thing. Here we go. Here's the expansion about this point, and it really describes a lot of nature that are more elusive just by disturbing simple things we know. So Patrick.
So I'm curious. So when you're trying to figure this out and looking at how, if I'm understanding correctly, how the perturbations essentially shift and move and change over time, are you looking at specific time scales? So you mentioned inflation, which, depending on who you talk to, is either like the split second that the universe was created or it's still ongoing, depending on which group of physicists you're going to talk to. But what kind of, I guess, time scales are you looking at? And also maybe length scales, if that's applicable in this case, considering we're, in this case, you might be dealing with the entire universe, then length scales might not make sense.
No, actually, length scales is actually like kind of the core of this entire problem. It's actually a great point to bring up because the entire thing with studying with large scale structure is that you're looking at like extremely large scales. So you're kind of ignoring, like, as funny as it is to say, galaxies are really small in this on the length scales you're really examining, because you're trying to look at not necessarily the distribution of galaxies, which you can also actually do as an application, but that's a different story. But you're trying to look at more like the distribution of uh, like like clusters of galaxies and sort of like things on like scales of maybe like 10 or 100 times larger than the size of galaxies. And so I think, like, to put some numbers in for people who want the details, I think we're looking kind of like more on the order of like about 100 megaparsecs and larger for these sort of like distributions, whereas galaxies I think are about 5 megaparsecs. Don't quote me on that, but yeah. So you're really looking at like really really massive scales, and the reason why is because it's really these scales that we see the homogeneity and isotropy of the universe. And so when we're doing sort of like the study of these perturbations, we want to sort of apply them only to those length scales, and because that's where we see these nice properties that we see in the universe. And in terms of time scale, that's also another interesting question, which is important for the research, because we're sort of like the difficulty in sort of in studying these perturbations is that in the early on, like you guys were saying earlier, you can sort of like Taylor expand and sort of like look at like linearized growth of these perturbations. But the issue is, as time gets longer and longer, then the evolution of this clustering goes from being well described by linear theory to becoming highly nonlinear. And so your standard perturbation theory actually breaks down very early on, and you can't actually use perturbation theory to kind of study how the matter evolves from the early universe to what we see today, which today is the only sort of data we can collect on matter distribution. So it's really important to make that link between how matter evolves from the beginning of the universe to what we see today. And because we can't do this typical perturbation theory, we have to sort of like develop all these new nonlinear methods, which is kind of like the core of the difficulty and why this field is kind of relatively recent. Because I think it was really 2010 that this study really took, or this field of nonlinear dynamics really took off, and people were able to really start getting a good amount of information from studying this nonlinear clustering from the beginning of the universe and comparing it to what we have today.
So that's where your research comes in. Then you're not doing this, and you're not standard cosmology, the stuff that you see in textbooks. So what are you doing to, I guess, how does your work relate to this nonlinear dynamic stuff? And you're trying to understand it more now that this time scale doesn't evolve linearly anymore.
So what we have, and like what my supervisor has done, is that they've created sort of like this more quantum field theory approach to sort of studying how these perturbations have evolved over time. And so what they have is that you kind of assume you have some sort of small perturbation, and then we have some really, really complicated function that kind of maps, that kind of gives like a very rough mapping of the universe at the early times to what we have now. And using this formalism, what I'm really trying to do is kind of apply it and see whether or not the formalism that they've created really matches with the sort of like distribution of matter that we see today. Because you can sort of assume your initial conditions, you can use the equations that they've made to sort of see what the distribution of matter, or like the probability distribution function of the distribution is like today. And so I'm kind of there, kind of filling in the steps, making sure it's fun, and then comparing that to results.
So 2 questions from that. So you talk about the distribution of matter and trying to model that, seeing if everything essentially matches what we have today. Are you including dark matter as well?
It's always a,
Or
or sorry, yeah.
no, just as someone who used to study dark matter, I feel that needs to be asked.
So as always, yes, the final result of all of this is to eventually be used to study dark matter, because with regular matter, we can see it and everything. But the end goal is kind of like once we have like sort of like an understanding of how matter is distributed, then the next step is sort of to apply that to galaxies, because with galaxies, they kind of like act as bias sources, because wherever you see a galaxy, you see a large collection of matter. And so you can sort of have this sort of like non-trivial relationship that relates the distribution of matter to the distribution of galaxies. And so once we figure out whether the formalism works for matter distribution, we want to do that and apply it to galaxies. But then you can take it a step further, because you know that while matter has a lot of, or while galaxies sort of have a lot of matter and sort of act as like a bias towards that, dark matter actually acts as sources for gravity for galaxies to form around. And so then we can kind of repeat the same steps that we did for matter to the galaxies, and do that for galaxies to dark matter now, which kind of gives us a better understanding, or we hope, of like properties of dark matter, how it's distributed, and maybe even like the statistics during the early universe.
I think I've said this before in this podcast. Or have I definitely told Liam this before, but I have to look around when I say this, because I'm at Queens and surrounded by Snow Plus people. But I'm one of those dark matter non-believer. But
You don't believe in anything.
Well, I believe in the one electron theory.
Oh,
Not
no.
really. But,
Oh, no.
no. But, well, I mean, I think there. Well, okay. I just don't like I would love to be wrong about dark matter, that people actually found it, but I think they're not gonna. But one of the main reason is that there is kind of hidden variable kind of type of solution again. Like, oh, of course there must be something that we don't see that deal with this, rather than try to amend general relativity, which is going to be a difficult thing to do. That to just account for those phenomena, which I think that could be right. They could find dark matter, but I think it's just it's a more beautiful description without it of the universe, in my opinion.
Well, I think they found, like, they they found dark matter in some sense because there's
No, they found the phenomena that couldn't be explained, right? The how fast the edge of galaxies move is faster than predicted, or there might be some mass that we don't see. That I think that's one of the strongest evidence of dark matter.
you can see like you can indirectly see invisible mass through telescopes and lensing, and the fact that there should be gravity where there's stuff where there isn't matter. So yeah, we kind of know it's real, but we don't really know what it is, I guess.
Okay, there is more evidence than just the rotation of galaxies for dark matter, such as from the cosmic microwave background. There's a whole bunch of stuff, a whole bunch of calculations that have been done where it shows, oh, this is where the matter is, and then there's this whole other thing that's dark matter, just from the cosmic microwave background. And also there's gravitational lensing from places where there's obviously no electromagnetically interacting matter there. So there's a lot of evidence for dark matter, whether it exists in the form of like a WIMP or an axion or whatever, is questionable and might be part of the reason why I don't do that research anymore. But dark matter, I would say with like a very good confidence does exist in some form, just maybe not in the form that people think it is.
Yeah, we don't know what the form is. We just know it's there. And also, James Webb Telescope may have there's a nice PBS Spacetime video on this about we might have seen these so-called dark stars, which is something I've talked about before, where the stars that form due to dark matter. But I'll talk about that another time. But the gist of it is, yeah, we don't. I guess you're right, Feely. We don't really know what dark matter is, but we're pretty confident it's a thing.
Yeah, I also do want to add, like, there is even like because I kind of used to be in the boat where like I don't really know about dark matter and everything, but the more and more I look into this, the more I'm like, yeah, no, it's definitely there now. Especially because if you look at things like for example, I think it's called the bullet cluster, where it was kind of like the idea like we had two galaxy clusters that's kind of like collided with each other, and what would you expect if you had sort of like regular gravity there and not dark gravity, dark matter, is that the distribution of matter should have like sort of like grouped up in the center. But instead, you found that they kind of like kept moving away from each other, and they couldn't have followed this like heavy uh, amount of matter that we see in the middle of them that we can't actually see, but we can kind of measure that it's there through lensing. And so a majority of the matter seems to kind of just like, or the majority of the planets kind of seem to pass through each other, and they kind of didn't follow what we would have expected them to follow if it was just regular gravity kind of acting there.
Oh, that's why it's like it might be general relativity has some problem that need to figure out that maybe there's some stellar phenomena we are not aware of, and I just like to be skeptics on dark matter. It'd be nice if they found it, but we'll see.
Well, I don't think general relativity disagrees with dark matter, because dark matter is just matter that you can't see, so it obeys all of the general relativity stuff, right?
Well, yeah, but it's a solution proposed to that rather than try to. Well, I mean, there are a lot of people try to amend general relativity with futile effort so far. So, well, maybe in the future, the description will be different.
Anyway, aside from dark matter and opening up that can of worms again, sorry about that. For the work that you're doing, I did mention the cosmic microwave background, and we discussed it in the intro topic. So, for your initial conditions to essentially grow and see how it compares to the universe as it stands today, are you using initial conditions, say, derived from like anisotropies in the CMB, or are you just kind of randomly making these perturbations and seeing how they play out?
So, well, actually, a lot of it actually is sort of like trying to figure out what the initial conditions are, because that's kind of like the big question that we're sort of doing all of this for, because we see what we have now. We're trying to figure out sort of like figure out how it evolved throughout time, and so we're trying to see if we can move that backwards and figure out what the initial conditions themselves are, because that's sort of like what the big question is that we don't know, which is what the initial conditions themselves are. And so in terms of, yeah, which actually that's also a whole can of worms that I could talk about it for hours because then there's a whole discussion as to whether or not the statistics for these perturbations are actually Gaussian or non-Gaussian and all that stuff. But yeah, it's not like we are kind of making an initial guess what the what the initial conditions are. We're sort of trying to work backwards to figure out what the initial conditions themselves are.
So I think this is a good time to pivot into your life a little bit because when I see someone who are in very mathematically rigorous field, it's always interesting to see how you got into it. So since you're doing your masters now, all right, what really got you into, let's say, in undergrad? Like, what got you into this type of cosmology or this kind of type of investigation rather than, let's say, like optics or the type of physics or even chemistry? What got you interested in these kind of stuff?
Yeah, I guess so what to add on to Feely's question, like during your undergrad, you did two different types of research. Actually, you started working in a lab, and then you ended up working on relativity. So I think what Feely said, I'm asking the same question, but also how did your undergraduate research tie into that?
Well, I think like having gone into my undergrad, I kind of had the impression that I've always kind of wanted to do more theory. But I thought, hey, I might as well just really try experimental for a little bit and see whether or not it's like, a hidden calling for me or not. But I think I very quickly found out I did not like experimental. Sorry. And so after having that, I was sort of like, more confident about like, yeah, I'm probably just gonna end up going to theoretical stuff. And that's where I ended up finding my supervisor for my undergraduate thesis, where I kind of worked with a little bit more like GR stuff. And I found myself enjoying a lot more and sort of boosted my confidence in wanting to kind of like do research in sort of like more theoretical stuff. As to why cosmology specifically, I found that cosmology was always kind of like the really cool but weird field in the sense that not only do you kind of just need to know about one thing, but you kind of need to know a little bit about everything for it because the universe just kind of started off at a very small size, assuming we believe in Big Bang and everything. But so because it was very small, quantum effects had to play a role there, and then it grew very very big, and now we have GR sort of playing a bigger role in sort of like the later history of the universe. And so cosmology is kind of like one of these weird things that are fields where you kind of need a little bit about from every kind of field. Like need to know a little bit about quantum and QFT, you need to know a little bit about GR and gravity and particle physics as well, because like to kind of like because of the particle physics as well is very important in the early part of the universe. Uh, Being able to like, kind of describe what inflation might be and everything. So yeah, it seems like it's a little bit of everything, and that's what I kind of liked about it.
So, okay, let me walk you further down the memory lane then. So, even before you undergrad, what really sparks you into get into physics or mathematics in general? Were you growing up like loving math, or because I always raise example with Liam that Liam liked insects and biology and stuff growing up, but look at what he does now. The a lot of people say what the wacky physics he does, right? So like, were you always like really good at math in high school? That's why you want to pursue physics, or was it came later on? What was your story?
I feel like I really liked math and physics like fairly early on. But like fairly early, I mean like probably like around the age of 14 or 15 or something. Because I know like I used to watch a lot of like more TV than I probably should have as a kid. But every time I would get bored from like flipping to like all these old cartoons, I'd stumble across like this like the Discovery Channel, the Science Channel, or something. And that kind of caught my attention, and I started watching a little bit more until I kind of realized, like, hey, this stuff's pretty cool. I kind of realized I kind of wanted to like maybe learn a little bit more about it. And then when I had the chance to actually do that, in school, I found that I did end up liking it and wanting and like try to work really hard in like those fields because those are the ones I found most interesting and kind of wanted to do the best at. And then with math specifically, math was a little interesting as well because I never saw math really like one of those tedious things to do, but I always found it like every sort of exercise is like a little game kind of play. Like for example, algebra, it's sort of like it's just a little puzzle trying to figure out what the value for X is. And so maybe having that kind of mindset's kind of pushed me more towards wanting to like either like focus more on it or like ended up changing my mindset and really viewing it as like a quote unquote fun thing to do.
Well, I get it though, because I used to help out with like math camps and stuff. So the problem sets are the problem we used to give kids or even given to us are like fun little puzzles, right? Because they are beautiful. Sometimes like there are a bunch of circle, you find this weird area, but there's a bunch of tricks you learn. So to me, it's really similar to solving like physical puzzles that show, but it's just abstract, and to me, there's much more degree of control you can have because it's just in your mind. You can come up with a wacky idea how to solve it, which I think foster creativity, which is really important in research, especially in theoretical research, right? I imagine when you do like solving your equations and stuff, it's not as straightforward sometimes. Sometimes you have to come up with strange ideas. Maybe I would do this method on here. Maybe I use this method in another field. And um, what was that like in your own research? Is it more like very standardized way to solve it, and then maybe numerically solve it, or is very what's called imaginative based idea where you have to try to throw many tools at it and try to figure out how to solve this really complicated thing?
Yeah, so I feel like maybe I don't have the right mindset for this, but I feel like at this point there's already been like so many different tools and uh, like really interesting approaches to do a lot of things that I kind of haven't. I feel like I haven't had the chance to really be too original when it comes to that because there's been so many other formalisms or things that exist. And so in terms of like my own sort of creativeness towards it, I feel like I haven't had the chance to really do that yet. But yeah, but in that sense, it's like yeah, like I do find that like there's always like a little bit of a toolkit that I have when it tries to sort of figure out this problem. Or like if the first thing doesn't work, I throw it out, I try something else, and I kind of go through that process until hopefully something works.
Well, actually, when I was listening to this writing workshop, there's a very good quote that really helped me. Was that we are not here to do original work, we are here to do valuable work, and I think that's really important, right? Because there are all these tools that over 100 years have been developed extensively, and why are we trying to be original? We can use it to solve the problem more effectively. So I think that's an important thing to note. So, in interest of time a little bit, so I'm going to move on. Instead of your past, look forward to the future. So, Liam mentioned a little bit about the hopes and dreams. This is one thing that we always ask our guest. So, what am I going to ask? This is a very loaded question, right? So, in the future, what are your hopes and dreams? So, what I mean by that is not like, oh, I want to be an engineer in 10 years. Like, who do you see yourself? You see yourself doing cosmology as a cosmological physicist, or you just don't I'm not sure yet, like what do you see yourself, do you see yourself doing a lot more math in the future as your dream, just sit down solving complicated equations and math, or what type of life do you see for yourself?
And I think you actually said it. I would like to really see myself sort of continuing with research and academia, especially within cosmology, because cosmology is like every once in a while there's this new development that's been happening in it. So there's a lot of still open-ended questions that I can kind of really see myself like really wanting to try and do and also working on in the future. And so yeah, I kind of see myself just like hopefully staying in and like sort of continuing down this line of like working in cosmology and sort of still doing this math, still doing some of the coding if I need, and hopefully maybe teaching as well if I have to. Yeah, like maybe just being a professor at a university.
So you're finishing your master's this year. Well, I guess this school year, right?
Yeah, yeah.
Yeah, so next year at some point. And I don't know, are you planning to continue through with Sergey with your PhD, or are you thinking of looking around, or are you just not sure yet?
Oh no, we actually recently talked about it, and like yeah, I think we both agree that it'd be good for me to stay and sort of continue the type of research that I'm doing with him, which is great as well because he's kind of like also like one of the big leading researchers in this type of field that I want to do. So
Yeah, Sergey's a big name. Everyone knows him. Even people I've met at conferences who shouldn't know him knew him.
That's scary.
Well, the thing about cosmology to more like a general public is that, especially when you're entirely theoretical, right? It's less heard of because scientists or physicists people hear of in cosmology are the one that are more famous because they here's the model they came out with it, and then there are thousands of other models that a lot of people, very intelligent people, worked on that just never seen the light of day. I remember, didn't we have a GR conference or something at our university? The bunch of like alternative theory of gravity, and almost every single presentation basically said, "Oh, Einstein is wrong, and here's the alternative way to look at it." And they're very rigorous and nice, right? But very few turn out to be somewhat agreeable with the experiment or measurable. So what do you think of the path forward? Is it I think everyone tries to find something that's measurable and agree with the experiment, or I think there's another side of cosmology where they just purely predict where we cannot find evidence yet. So would you like to look into those part or more the observable part?
This is the last thing. So this is the last thing, and then we got to move on for the sake of time.
Right. So sorry, were you kind of just asking like what I kind of think of like the current state of cosmology in the research, or
Well, I mean, like, in your interest, like, are you more interested in look at something measurable soon, or like something that's very like purely not really observable at the moment, but maybe in 100 years, maybe we can break the opacity somehow into the earlier universe.
I guess ideally I would like to do a little bit of both because it's very hard to get your ideas uh, accepted by the scientific community if there's no real way to really test it, or I mean, like, yeah, if there's no real way to really, like, sort of be like, here's my theory, but trust me, it works. But I don't really, yeah, but I don't really have like the evidence to show you. So yeah, it is important. If I do think it's a good idea to sort of work towards things that are more applicable towards being observed really early on, so you can kind of like build legitimacy for whatever theory you have. But that being said, as well, sometimes working like pure theoretical models, sometimes you just have to do it if you really get a good idea that might explain some, fundamental problem that still exists within the fields. So a little bit of both would probably be my approach for it.
Well, thank you very much for joining us today, Alex. It's great to have you and talk about your research a bit, some inflation things.
Thank you for having me.
Yes. So to end off the episode, Patrick's going to be telling us a story about the oldest things in the universe. But before he does that, he's going to tell you how to reach us, and he's going to ask you, Alex, how people can reach you if you would like them to.
Oh yeah, I guess if people want to reach me, there is my McMaster email, a university email, which I think you should be able to just find if you Google like McMaster physics graduate students, and then there's a whole list I think that they have with all their email addresses. So if you Google like McMaster physics graduate students and click on like the first link, there's probably going to be my name there as well as like my email address for anyone who wants to reach me.
Yeah, we can post it in our description too if you want, or if you don't want, that's fine.
That's fine with me.
And if you also want to reach out to us, we can pass your questions on along to Alex as well. You can reach us through email. We are hyperthesispodcast@gmail.com. You can ask us questions and questions for our guest, along with have comments, have suggestions for topics, or if you would like to be a guest on the show as well. We've had a lot of guests this season already and a lot more planned. So if you would also like to be a guest, we are more than happy to have you if you are an expert in your area. We also have an Instagram. You can follow us at The Hyperthesis, where we post updates when we're posting episodes, along with updates during our breaks, and other fun things to be interactive with the audience. You can also send us a DM. We check that as often as we check our email, if not more. So go ahead and send us a DM if you have episode suggestions or you would like to be a guest as well. We are also on YouTube. You can check up to the end of season 4 currently on YouTube. And they are very nice visuals. And if you spot the differences between the different seasons, then you will win the knowledge that you are a good fan of the show and watched all the YouTube videos. But regardless of how you find us or how you listen to us, whether it's on Google Podcast, Apple Podcast, Audible, or through Spotify, which we're based out of, feel free to give us a like, a comment, a subscribe, give us a rating, share your thoughts about the podcast. We are more than happy to hear and take feedback in about it. And again, if you have questions for Alex, you can either contact us or you can send him an email, which will be in the description for the episode. So moving on to the story, as Liam alluded to, we are going to be looking at some old things. And I was going to put a joke here, but there didn't seem like a good place to do this. So I'll start with saying that way back in episode 9, so long ago in terms of episodes, we did a story on observing the universe, ending it with a brief discussion about the James Webb Space Telescope that at that time had just launched and was starting to collect data. We also featured a couple episodes later, Parisa Nazari, talking about measuring things like space dust using such sensors as the James Webb Space Telescope, which, again, very exciting that we have it now. Now, more recently, we discussed observations made by the James Webb Space Telescope of galaxies that were just too old to exist in our current model of the universe and its age. And this sparked the question, what is the oldest object in the universe? And it's really nice that in our intro topic, we were kind of discussing how we can determine the age of the universe and talking about that throughout the main topic as well, and dealing with variables like that. But before going to the furthest extents of the observable universe, we'll start with this question by looking at Earth and what the oldest things are that we can find on Earth. Now, the average human life expectancy in Canada is just under 82 years old. However, the oldest person that's actually officially recorded was Jeanne Calment, who was 40 years older than the Canadian average, and she lived to 122 years and 164 days old. Now, for reference, the oldest Canadian was over 117 years old, but still 5 years off of the record. However, for animals, humans are relatively short-lived, especially compared to some even vertebrates out there. We see tortoises as synonymous with age, such as Adwaita, the Aldabra giant tortoise, who lived to the age of 255 years old, and we know that Greenland sharks can live up to at least 500 years. So that means there are Greenland sharks around today just swimming in the ocean that could have been around shortly after the Europeans came over to the Americas. Now, glass sponges are also a type of animal. They have been found to be more than 10,000 years old. That's impressively old, and compared to the oldest tree in the world, which is known as Methuselah, which is a bristlecone pine, that's more than doubles its age, because it's just under 5,000 years old. Now, moving from living to the inanimate, let's talk about rocks. Rocks undergo changes over millions of years, and this means that a lot of the rocks that we have today haven't really been around for too long, especially if you look at rocks that are recently formed in the crust, such as the Mid-Atlantic Ridge. Those are quite new rocks, but we do have very, very old rocks too. And some of the rocks that we have found are over billions of years old. And we are able to use various dating techniques, especially uranium-lead dating, that's able to determine the age of these oldest rocks. Now, the oldest rock that we've ever found is actually in Canada. Up in the Northwest Territories, in the Acasta Gneiss, is a region of rock that is estimated to be about 4.3 billion years old. That's quite the jump from from these sponges, which are 10,000 years old, to these rocks on Earth that are 4.3 billion years old. Now, the oldest terrestrial material, don't ask me about the definition, I'm not a rock guy, but the oldest terrestrial material we have found so far is a zircon mineral that is about 4.4 billion years old. So about 100 million years older than the oldest rock that we found. Now, of course, there are uncertainties with these numbers, but these are approximately how old they are. And this 4.4 billion year old piece of zircon was found in the Jack Hills of Western Australia, which is actually a place that's well known for having old rock formations. Now, turning our attention away from the Earth and into the night sky, we see the Moon, which is estimated to be about 4.53 billion years old, and common theory now suggests that it was formed when Earth collided with a Mars-sized planet called Theia, and this ejected a bunch of mass, which then formed the Moon. Now, the Sun formed around this same time, just a few tens of millions of years earlier, allegedly, around 4.56 billion years ago, along with most objects in the solar system. Now, there have been older objects discovered in the solar system, because all of it came from something, such as meteorites that have crash landed onto the Earth. The oldest meteorite that was discovered on Earth so far has been about 7 billion years old. That's older than the solar system as we know it. Now, to see items even older than 7 billion years old, we have to look outside our solar system and past essentially what's kind of close to us, looking past exoplanets and the Oort cloud and all of that, and look at stars. Now, we can estimate the age of stars based on many of their properties that we can derive from light, such as the intensity of the light or what's contained within that spectrum. And a lot of the older stars will be metal deficient. So these older stars formed in a time where there weren't as many metals present, which of course are formed from stars burning for too long and dying and going supernova, and their cores getting more and more metal rich and producing these metals. So these very metal poor stars are great indicators of old stars. And unlike the sun, which was formed again about 4.53 billion years ago, we can look at a star that's about 190 light years away from us and is estimated to be about 14.3 billion years old. So this is a strange number because, as we discussed, we kind of know the age of the universe based on a couple different measurements, and it's about 13.8 billion years old. And estimates for the age of the star are saying that's about 500 million years older than the age of the universe. Now, of course, there is some uncertainty, so it's 14.3 billion years old, plus or minus 800 million years, but the fact that we've arrived at that number in the first place is quite astonishing. This is kind of paradoxical and has led to a lot of debate of, is the universe actually the age we think it is? And we can't really just ask the universe for ID. We have to do a lot of complicated things, such as what Alex is doing to try and figure out, okay, what happened at the early formation? What's going on a universe-wide scale? So far, this star, known as Methuselah, also, because apparently all old things get named Methuselah after a biblical person, it's the oldest known object in the observable universe. We have yet to observe something older, and keeping in mind that there are some things that we just can't observe or determine their age of, such as black holes. It's very hard to determine their age based on just looking at a black hole. We can kind of estimate it based on stuff that's around it, but it's complicated. So we have this oldest object, and we're now discovering other old objects within the universe. So the oldest galaxy, called Maisie's Galaxy, which was actually named after an astronomer's daughter because it was discovered on her birthday, it's one of the oldest galaxies found so far and was formed less than 400 million years after the Big Bang. Now, the age of the universe itself is predicted using several methods, which we discussed about beforehand. But findings from the James Webb Space Telescope, which is able to see further away from us, and so therefore further into the past, is making us kind of reconsider the age of the universe and relook at the calculations that we've based our age estimates on, and trying to figure out, okay, how can all of this be possible? How can these galaxies be forming so close to the Big Bang, but show similar complexity to galaxies that took billions of years to form? So there's a lot of questions that have yet to be answered. And who knows what we'll see with new observation techniques including new telescopes that will be in space and on Earth, as well as recent and future advancements in gravitational wave observations. We may see from all this that our thoughts about how old the universe is actually changes, and as we see further away and therefore further back in time, who knows what we may discover.
Thank you very much for that, Patrick. Yep, the universe got to be older, or the physics we understand about galaxy formation and all that jazz has to change, or our models have to change at least. So thanks everyone for joining us today for our 61st episode with Alex. We'll see you in the next one.
All right. Thank you very much, Alex. Take care.
Thank you, Alex. Bye, everyone.
Bye.